Sometime last year, I started getting really interested in microwave plasma, which can be made by microwaving certain things like a lit match, aluminum foil, or just a couple grapes. When it's done properly, a lot of hot gases are formed, and some of it can be heated even further by the microwave to the point that it becomes plasma. In a lot of videos that I found online, the plasma that formed was allowed to float freely to the top of the microwave, where it usually just quickly disappeared. In other ones, though, the plasma was trapped in something like a cup or a bowl, and it was able to stay there as this CGI looking fireball. I was really curious to know more about what was going on, but when I looked it up, the info seemed to be really lacking. Most of what I found was either really vague or just speculation, and there was almost nothing on the formation of the plasma ball, which was what I thought was the most interesting part. About 6 months later, though, I started to get some answers when Veritasium posted a video about grape plasma. In this video, he explained in detail how and why grapes make plasma, and he also explained, at least for grapes, where the plasma ball was coming from. Apparently, under the extreme heat, some of the sodium and potassium ions in the grapes can get vaporized and then heated to the plasma state. I thought that the explanation was quite satisfying, and it answered pretty much everything that I felt I needed to know about grape plasma. However, it actually made me a bit more confused about the plasma that came from other things like matches or aluminum foil. In every video that I saw, the plasma ball that they produced was yellow, just like the grape. In the grape, though, the yellow light was being emitted by sodium ions, but in these things, especially the aluminum, there should be little to no sodium. So, where was this yellow plasma coming from? To me, this was a genuine mystery, and I really wanted to get to the bottom of it. So, I decided that I'd try to investigate it and to see if I could come up with some sort of an answer. I also thought that it was just a decent excuse to just have fun and play around with plasma and to maybe ruin a few microwaves. Before this, I'd never made any plasma in the microwave, so what I wanted to do first was just try it out and to kinda get a feel for it. To make the plasma, I had the option of either using a match or something metal like aluminum foil, and I felt that it was probably safer to start with the match. So I put a match on a watch glass, lit it on fire, and covered it with a beaker. Then I turned on the microwave, and well, it actually worked. It looked just like the CGI fireball that I saw in all the videos, and it also made a characteristic sound. One thing that I noticed though was that sometimes it would shift more towards being blue, which was something that I hadn't really seen before. All this plasma was incredibly hot, and I was worried that running it for a while would crack the beaker, but it apparently didn't have any problem at all. I thought that maybe this would go indefinitely as long as the microwave was on, but after about 30 seconds, it ended up just fizzling out on its own. When it was done, I expected the entire beaker to be burning hot, but it wasn't that bad. I was able to pick it up by the lower part where the plasma didn't directly touch, and it was only just slightly warm. I then did a few more runs, just to see how reproducible it was, and it worked every time. However, the time that it lasted for seemed to be pretty random, and sometimes it would disappear relatively quickly. For each run, I didn't use the same beaker because I didn't want to damage it by overheating it. So every time I got a new beaker, and I put the hot one on the side and let it slowly cool down to room temperature. As it did this though, the gas in the beaker took on a faint yellow color, which was caused by the formation of nitrogen dioxide. I thought this was really cool because it showed that the air in the beaker was getting extremely hot. Nitrogen, which is N2, represents about 80% of air, and the bond between the nitrogen atoms is extremely strong. So, under normal conditions, it really doesn't like to react with many things, and it's often used in chemistry as an inert atmosphere. Under extreme heat though, above around 2000 C, some of the nitrogen molecules get split apart, along with some oxygens. This allows them to start combining with each other and to form colorless nitric oxide gas. This nitric oxide then reacts with even more oxygen to form the orange nitrogen dioxide. A lot of the oxygen that split apart ended up combining with nitrogen, but some of it also combines with itself. This leads to the formation of ozone, which is an extremely strong oxidizer. Most of it ends up reacting relatively quickly with the nitric oxide, but some of it is still left over afterwards. It doesn't have a distinct color like nitrogen dioxide, but its odor is extremely potent, and I could sometimes smell it when I open the microwave. Besides just the color, to further confirm that nitrogen oxides had actually formed, I did a fresh run, and then I put the beaker over some wet pH paper. If there were oxides there, they'd be able to dissolve into the water and form acids, and turn the paper red. The effect wasn't as drastic as I hoped it would be, but there did end up being a color change. This formation of nitrogen oxides and ozone told me that at the very least, some of the air was probably getting heated to the plasma state. The purple light that it would normally emit, though, was being completely dominated by something else. So, now that I knew that it worked, the next step was to try to get a better look at what was going on. I mean, it was possible to mostly see what was happening through the grating, but it just wasn't good enough. I really needed a nice and clear shot of it, and to get this, I had to somehow film inside the microwave. There was actually surprisingly little information on how to do this online, and I ended up having to get help from Steve Mold, who's another science YouTuber. He found that there were two main ways to do it, either by using some camera tricks to make the front grating almost disappear, or by drilling a hole in the microwave and using a smartphone. Each method comes with its own list of pros and cons, and if you're interested in knowing more details, Steve has made an in-depth video on his channel. For what I was doing though, I felt that the smartphone method would work better, so that was what I went with. To do this, the first step was to drill a hole, and I figured the best spot was at the back because this would not only give the nicest shot, it was also the thinnest section of metal. I didn't know exactly where the best place to put the hole was, but I figured that I would just start by making it dead center, and then I could maybe adjust it from there. The microwaves in a standard microwave oven are relatively big, and their wavelength is around 12 centimeters. And in theory, I could probably safely make a hole as big as half their wavelength, or 6 centimeters, and not really have any of them leak out. However, my biggest concern wasn't really safety, and I was more worried that if any leaked out, it could mess with the camera sensor. This could of course cause some damage to it, but I was more concerned that it would just make the video unusable. So just to be sure, for the sake of the footage, I tried to make the hole as small as possible. To attach the phone, I found that the easiest way was to just use some aluminum tape. However, getting it to stay there and to line up properly and keep it all straight was still a bit of a pain. The phone that I was using here was the Samsung S7, which was actually in mint condition just a few days before filming this. Tragically though, I had slipped on a wet floor while my phone was in my hand, and I ended up slamming it really hard and exploding the screen. I think I also almost broke my elbow, but thankfully, it didn't damage the camera at all. With this now ready, I flipped around the microwave and took everything out, and I also turned over the glass tray so that it would no longer rotate. I did this because I wanted to get the shot as clear and stationary as possible, and I didn't want to have the beaker spinning and moving around. After this, I figured it was just a matter of running it and getting the footage, but it turned out to be trickier than I thought. I tried doing it several times exactly the same way that I had done it before, but it just refused to work. I started thinking that maybe the match was just going out too quickly, so then I tried it with a huge pile of matches, and it still totally failed. I then tried it a couple times with a candle, and it didn't look like it was doing anything. After this, I started getting a lot more creative with it, but I was basically grasping at straws at this point. So the question now was, why wasn't it working? And there were only two possible reasons. It was either I just got really lucky before and it worked every time, or it was because I took away the rotation. To test this, I flipped the tray back over and tried it again, and well, it started working. This run, about halfway through, also ended up having a pretty cool effect. I then tried it a few more times just to make sure that it was consistent, and it worked every time. From this, the rotation was clearly very important, and I was honestly kind of expecting that to be the case. This is because in a microwave, the electric field isn't distributed evenly. All the microwaves are bouncing around and resonating inside the metal enclosure, and at some point, almost all of them end up colliding and interfering with each other. If the waves collide and they're more or less in phase with each other, they can add together in a process known as constructive interference. At the points where this happens, the electric field becomes stronger, and it has a stronger heating effect on food. If the waves are out of phase when they collide though, they'll interfere destructively, and the resulting electric field at that point is weaker than before. This makes it so the microwave is filled with a bunch of hot spots and dead zones, which can obviously be a problem. To try and get around this issue, there are a few things that can be done, but the simplest way is to just add a rotating tray. This way, whatever you're trying to heat up will pass through both dead zones and hotspots, and they'll kind of even each other out. In my case though, if I didn't want to use the rotation, I would somehow have to make sure that I always put the match in one of the hotspots. I spent a bunch of time trying to fix this problem, and one of my solutions was to use some thermal paper to map out the heating pattern of the microwave. Then from this, I was able to mark down on the tray exactly where the hotspots were, and it did end up working. This whole endeavor ended up being a waste of time though, because after doing a couple runs, I suddenly realized that there was a way easier and better method. All I had to do was completely take out the tray and to directly use the rotating plastic thing. This way, it not only gave me the cleanest shot of what was going on, it also fixed the entire issue with rotation. Without the tray though, it was much lower than before, so I had to drill a new hole in the back, and the old hole was covered using aluminum tape. I also made the hole a lot bigger than before, and I bought a new phone to get better footage, and so that the screen would stop cutting my fingers. Then, when it was all set up, I gave it a try, and it worked really well. Some of the runs still died out a bit quickly, but for the most part, it seemed to be really consistent. So now that I had a clear view and a good setup, I felt that I was ready to try and figure out what was going on. I originally planned to completely skip trying it with grapes because it was already heavily covered by Veritasium. However, I decided that it was probably a good idea to start with what was already known and then to build up from there. From the paper that Veritasium covered in his video, it was made clear that it wasn't necessary to cut the grapes in half and that it was possible to just use 2 full ones. From what I could tell, it also looked like they didn't rotate anything in their trials, so I kept it stationary as well. However, after trying this a couple times, it mostly just made a mess, and I never got any sustained plasma. The only thing that I found to work consistently was to first shoot the grape with a torch to get rid of most of the water. This way, it made way less steam, and the plasma ball that I got looked exactly the same as all of the videos that I saw online. It was strongly yellow, which was apparently from vaporized sodium ions, and there was also a hint of purple coming from potassium. To really confirm this though, I borrowed this thing from my dad, which was a visible light spectrometer. With this little box, I was able to analyze the spectrum of light that was being emitted by the plasma and split it apart into its components. When I did this for the grape plasma, this was what I got, and it was exactly in line with the existing data. The biggest peak was at 760, which corresponded to potassium, and there was a small peak around 590, which was from the sodium. The size of the peaks here tells us the relative amount of light that was coming from each of them, and because the sodium one was smaller, it meant that it was contributing less. Despite this though, it still ended up looking yellow, because our eyes are much more sensitive to this light than what was being emitted by the potassium. So now, going back to the match plasma, the sodium and potassium theory didn't seem to really fit. The typical match head contains a bunch of different things along with potassium salts, and it shouldn't really have any sodium salts. So, I would think that the plasma would be more tuned to the color of potassium, which kind of looks purple. However, despite having pretty much no sodium, it was still distinctly yellow. Another weird thing was that unlike the grape, the yellow color never lasted for very long, and if the plasma were sustained, it would shift to being blue. This made me think that what was happening here was probably just incandescence of hot soot. In a typical wood fire, like with the match, the orange-red color of the flame is coming from the hot soot and other small particles. As the wood releases them, they get heated up by the reaction, and then at some point when they get hot enough, they start radiating some of their thermal energy as visible light. In the visible band, red light has the lowest associated energy, and that's why things start out as being red hot. As the temperature of something increases though, the energy of the light that it emits also increases, and the color slowly shifts. At a certain temperature, there's eventually a balance between blue, red, and green light, and our eyes perceive this as being white. However, if it gets even hotter than this, then it can start looking blue. So I thought that maybe the hot soot in the match flame was just getting pumped by the microwave and turned into some sort of really weird incandescent bulb. Then maybe as it sat there, soaking up energy from the microwave, it just got hotter and hotter and slowly shifted to being blue. This made total sense to me, and to confirm it, I took a reading of both when it was yellow and after it had turned blue. Then I took a look at what I got, and I was really surprised by what I saw. The spectrum looked almost exactly the same as the grape, except this time, the sodium spike was even bigger. The largest spike, though, was still from potassium, which was probably from the potassium salts that were in the match head. Now looking at it when it was blue, the only difference was that the baseline was bumped up by the incandescence of the hot soot. Visually though, this was mostly able to mask the yellow, and it made it look like it was disappearing, but this clearly showed that the yellow was still there. So, my incandescence idea was kind of right, but it was only half of what was happening. Apparently, the plasma still contained a lot of sodium ions, but this didn't make any sense because there shouldn't have been any there. This made me think that maybe it was possible that my match brand was just weird and decided to use some sodium salts as well. I tested this by trying it with another brand, but the result was still the same. From this, I was now thinking that they maybe did just have sodium salts in them, and I should be trying it with something else. So I figured that the next best thing to try would be with metal, which I knew wouldn't have any sodium. My first attempt at this was with a bunch of forks, because I'd always heard that it was dangerous to put them in the microwave. However, they really didn't work very well, which honestly kind of surprised me. I was able to get them to spark a bit, but there was nothing even close to a sustained plasma. I then tried it with some loose aluminum foil, and I was actually able to get it to work. The initial color that it made was a nice blue, and this was what I expected for what was probably a mixture of plasma from aluminum and air. What was weird though was that the blue color never seemed to last for very long, and it always would somehow turn yellow. However, there really shouldn't have been any sodium here, especially just floating around in the air, so this time, I figured it had to be from something else. So again, I got out my spectrometer and took a reading, and this time, there was somehow even a bigger spike at 589. This small spike in purple was from the aluminum, and these other spikes were mostly from the air plasma. They were responsible for the initial blue color, and apparently even after it had turned yellow, they were still there. They were just getting completely overwhelmed by the yellow light, and it made it look like it disappeared. After seeing this, I thought that maybe my aluminum was just contaminated, so I ran it with steel wool and some pure zinc granules. I then got the spectrum for both of them, and I died when I saw that there was still this massive sodium spike. Now at this point, I felt that there were two main possibilities. Either everything that I had was contaminated with loads of sodium, or just maybe the yellow light was actually being caused by something else. And if this were the case, it would have had to be coming from something that was common between every run, and the only thing left really was air. So I went online and started grasping at straws for something in air that might be able to make a yellow light. Surprisingly, there actually was something, and I found that the reaction between nitric oxide and ozone to make nitrogen dioxide was actually chemiluminescent. From before, I knew that this reaction was definitely happening, and apparently, it released yellow light. Chemiluminescence can sometimes be monochromatic, and I thought that just maybe the yellow light that it was letting off was coincidentally really close to sodium. It was possible that maybe things were just going in a cycle, where the gases reacted together and released light, and then got torn back apart by the heat. To test this, I set up an electrical arc, and I saw that there was yellow light being released. I then took a reading of it, and this time I was hoping that there would be this big nice yellow spike, but no, there was nothing. After seeing this, I was officially stuck, so I reached out to Ben over at Applied Science, and I desperately sent him way too many messages. Initially, he suggested what I originally thought, that it was just incandescence or maybe some sort of sodium contamination. But then, I sent him some of the spectra that I took, and his reply made me instantly facepalm. He suggested that the sodium might not have been coming from the match, the metal, or any sort of contamination, and it might have just been coming from the glass. This was something that had never even occurred to me, because in my mind, the beaker, the dishes, and the watch glasses had nothing to do with the process. They were just convenient things to do this with, and there wasn't much else that could both withstand the extreme heat and also be transparent. On top of this, for pretty much everything that I do, I'm always assuming that the glass is pretty much completely inert. Glass in general, though, is usually at least several percent sodium oxide, and it was very possible that this was a major source of sodium ions. I now had a new lead, and I figured that an easy way to test this was to make a really concentrated solution of potassium chloride. I then sprayed this on the watch glass, the aluminum foil, and all over the inside of the beaker. This way, if any ions were going to get vaporized, it would preferentially be potassium. Because of all the water, things were a bit harder to get started, but when it did, it was clearly purple. I took a reading of this, and there was pretty much no peak from sodium. I then let it run for a while, and as it sat there, it slowly got more and more yellow as it ionized the sodium in the glass. In my opinion, this was pretty good evidence, but to really confirm it, I had to find a way to do it without anything that contained sodium, and this was what I came up with. For the plasma source, I used aluminum because I felt that it was the most consistent and easiest to use. It gets really hot though, so to hold it, I used KO wool, which is an almost sodium-free, high-temperature ceramic fiber. For the container, if I wanted it to be transparent, I didn't really have any options besides plastic. For my first attempt, it actually worked quite well, and I was able to get a sustained blue plasma, and it didn't look like it was turning yellow. Unfortunately though, I was too slow to get a good reading, and it ended up melting. For the second attempt, I used a much thicker cup, and I was able to get the spectrum. This time, I saw all the peaks from the aluminum and the air, and there was pretty much nothing from sodium. After this, I went back and did it with the match, and it still ended up containing sodium. This initially surprised me a bit, but after thinking about it for not very long, it made a lot of sense. To increase the friction of the match head, and to make it actually possible to ignite it by striking it, there's a lot of glass powder that's included in it. I think that this is the major source of the sodium content, but to a certain extent, it might also be coming from the wood itself. Either way though, the initial amount still probably isn't very much, and once it's sustained, most of it ends up coming from the glass. So now, from all this, my general conclusion was that there were two main parts when it came to making microwave fireballs. The first part was the initiation, which determined the starting color of the plasma. With the grapes and matches, it was yellow because it was made from sodium and potassium ions. With the aluminum, though, it was blue because it was from the emission of aluminum and air. Then there was the second part, where this initial plasma started pulling sodium ions from the glass, which either shifted it yellow or made the yellow a lot more intense. This color change usually happened after the plasma had already made it to the top of the beaker. Sometimes though, usually when things got really hot, a lot of sodium ions were able to jump into the aluminum plasma as it was forming. This would give it a much stronger initial yellow color, and it would hide a lot of the nice blue. With the match, there also seemed to be some incandescence going on, which was often able to mask the yellow. This added another layer of a way to potentially control the color of the plasma, and I feel that it could be fun and interesting to try to come up with some cool shifts. Changing the starting source or including some sort of additive is probably the easiest way, but I think that it also might be possible to modify the glass. Ben has a cool video where he exchanged the sodium ions in the glass with potassium ions, and I think that could have a cool effect here. It should cause it to shift to a purple color instead, and maybe if this works with lithium, it could cause it to change to a really nice red. For now though, I think I'm kind of done playing around with plasma, and I'll leave that up to someone else to try. Now, one last thing that I wanted to address was the distinct sound that the plasma made. The major reason for this is that the microwave doesn't pump out microwaves continuously. It instead does it in pulses, and the plasma was only getting energy around 120 times a second. In slow motion, this is much easier to see, and the plasma is constantly expanding and contracting. This generates pressure waves in the air at the same rate of 120 Hz, which we then interpret as sound. To confirm this, I just played the sound, and I used a tuner app that I already had on my phone, and it came out at 120 Hz. But anyway, I think that's about it for this project. In the end, the answer to my little plasma mystery turned out to be way simpler than I ever expected, but I still thought that it was pretty satisfying. There are of course a lot of things that are still unknown about this whole process, but I now feel that I finally have some sort of decent idea of what's going on. I do honestly feel a bit foolish though, for taking so long to figure it out, where now in hindsight, it seems like such an obvious answer. In this video, I was only able to cover the main things that I tried, but there were a lot of other cool clips that I got. This one in particular was my favorite, and it was my first attempt at making the sodium-free plasma. I also ended up damaging a couple microwaves by doing things like heating it without a bowl to capture the plasma. Most of the time it ended up just quickly disappearing, but there were a couple times where it was able to stick around. I let it run for a decent amount of time, but when the metal started getting red hot, I kind of wimped out and ended up stopping it. I also tried a couple times to heat things directly on the plastic rotating thing, which caused it to light on fire. Then, once it was all charred and burned, it would light itself on fire every time the microwave was turned on. To make it functional again, I had to break off the plastic piece and clean things up, but this meant that it was no longer able to rotate. With all that being said though, I do think that with some basic precautions, it's possible to safely make plasma in the microwave, but still, I really don't recommend it. I also don't recommend drilling any holes or trying to mess around with microwaves in general, so please don't try to do that either. But anyway, I hope you enjoyed this project, even if it was a bit different than the stuff that I normally do. I did really enjoy, though, trying to get to the bottom of some sort of mystery, and I would love to try it again. So, if you have any other mysteries like this of your own, I would love to hear about them in the comments, and I just might actually cover it. As usual, a big thanks goes out to all my supporters on Patreon. Everyone who supports me can see my videos at least 24 hours before I post them to YouTube. Also, everyone on Patreon can directly message me, and if you support me with $5 or more, you'll get your name at the end like you see here.